hosting something like that.
Oh,
Oh,
it's live
yeah,
stream now.
yeah,
So
yeah, we're on YouTube now, so we have to be nice.
we have to be nice. No one cares about our personal stuff. So.
So anyway, oh, which reminds me, Greg, um, did I? No, I probably didn't. When you send me an email, I'm going to send back to you. I did a little write up on my sewer scope.
Oh, guy published it in the St. Pete
Oh,
News.
okay. I don't need to give
Yeah,
you that. Okay, yes.
yeah,
So
it was good. Did you sell it?
I couldn't get any takers, and you know what? It was very home built with whatever I could get my hands on. It had a lot of quirks to it, so I still
Okay.
have the optics.
All right.
Uh, so yeah, anybody want 6-inch f10 optics, 1-inch diagonal? Talk to me. Needs to be recoated because the original coatings from when I got it from Jakers in 1986.
I got enough telescopes.
I know.
Yeah,
Yeah.
me too, as you could tell from my first slide.
Well,
Well, I'm glad to see
I'm
you
a
back on
mead
your
man.
travels. Interestingly enough, Ken, Ken Poshedley, you have two squares in our bunch of squares here. I don't know how you got two personas, but tonight you have two personas.
Split personality.
I, I can think of other things to say about that, but none of them are appropriate for YouTube.
I'll tell you, I was really impressed with that solar that that solar unit. What is it? Solax?
ML
Helium.
Astro.
Huh?
That ML Astro.
Yeah,
Yeah.
that ML. Oh my
Yeah,
God.
I was looking at that. I'm gonna get one of those.
That's gonna revolutionize. No one's gonna want an H alpha scope anymore because you can
Yeah,
just have your
yeah,
regular
Well,
refractor, 80
yeah.
millimeter or larger, put
Yes,
that on
yes,
there, and you have every wavelength, H alpha,
yes,
calcium,
yes, yes.
rhodium, you name it, you got it. I mean,
well,
I got a beautiful 80 millimeter stellar view I can put it on.
yeah, yeah,
well,
that's what I mean. That's what I think people will be doing.
the funny thing is, I've seen a write up of that, and I can't figure out where now. Was that published on something like that on Cloudy Nights or?
Now you don't need a filter in front of the scope, do you? In front of the sunlight just comes in, right?
I wouldn't think so with an 80 millimeter.
Yeah, there's no pre-filter. I mean, on top.
Yeah.
Yeah, that's what
All
I
right.
thought.
Anyway,
I have an H alpha scope.
Yeah.
I think it beats the pants
Do you
off it.
think other companies will start making these?
I remember that. Like, yeah, but I also remember hot potatoes being like, you have to pass it and be the one holding it.
What'll happen is that Solex will become mainstream. You'll see Lunt and Daystar and all the other H alpha companies, probably even Skywatcher and Celestron will have their own versions of it. And the price will probably be about the same. I don't think it's going to go down much. They'll keep it around $880, $1,000 or so. And
does that design have a patent? Does that design have a patent on it?
I don't know.
No, I don't think so.
Well, someone's going to get a patent. Someone's going to patent it. That's for sure.
The
Solex is freeware.
Okay.
Oh wow. Yeah, John, that was an excellent presentation. My God, that thing is really something.
Thank you.
Yeah, I had to bail out, but I'm going to look at the YouTube recording later on tonight.
Yeah.
Yeah, everything's on YouTube right now, both days.
Yeah. So.
Say, John, your presentation was excellent. I think the thing that clinches it, I've already pre-ordered one, by the way. I think.
All right.
I think I have I have an H alpha scope and I've used it and I like it, but I think this is what clinches it for me is when you make, I think it was your last slide where you make the side by side comparison between the ML Astro and Coronado. I mean, that like holy cow. That
Yeah,
just
Coronado has always been like the best out there. And when this thing just walks all over it, that says everything right there.
It'll walk all over the other ones, Lawn Daystar.
Oh yeah,
yeah.
absolutely.
Well, I've
So
got Daystar stuff. One more thing, John, if I may. I think that slide and the final slide that your friend, I think Wab put it together. The
mhm.
one that has all the different,
All the wavelengths.
all the way links. That's
Yeah.
superb.
Yeah.
Yeah.
A real convincer that I think the serious amateur, or even I'm a teacher. I think this kind of thing is just jazzes my students when they see this kind of stuff.
Yeah. And the thing is, Lunt has 4 different frequency filters. They have hydrogen alpha, calcium H, sodium, and magnesium. Well, and they got helium. That's 5. This thing has dozens of frequencies, and it's $800 versus almost $2,000 a piece for the quarks. For the Lunts, they're up running around $2,500 for a 60 millimeter now. So yeah, as far as cost, this thing's just crazy incredible.
Yeah, I
I'm going to give
volunteered
her.
at the
I'm going.
Space Museum and downtown in DC. And when it's cloudy, we're inside and I'm showing SDO images. And, you know, it's nice. We've got SDO images at several wavelengths. But even though that's nice, this really just blows it away.
Yeah.
Yeah.
I'm going to give everybody a couple minutes to log on. So probably about 3 minutes after the hour is when we'll start.
Okay.
And remind everybody to be on mute for everything, unless you have something to say.
I've got a suggestion. You know, it wasn't too long ago that Meade went out of business, and maybe we should give a moment of silence for its demise. Orion Telescope had bought them, and they closed up shop. They were down near Santa Cruz about 6-8 months ago or so. So, unfortunately, Meade is gone, unless somebody
Did you hear my
bought him out of
lecture?
bankruptcy.
Did you hear my lecture on the Mead resources and repairs?
Huh?
Did you hear my lecture earlier? Mead resources and repairs. That's
No.
what I do. No, you didn't. Okay, watch it on the pre. That was a good idea. I should have said that. Let's have a moment of silence for me. Yeah, I gave a whole
Yeah, I have
lecture.
a Meade 10-inch Schmidt Cassegrain. Been using for almost 40 years now.
You need to listen to my lecture. I talk about resources to get hand controllers and accessories and 2 people that will repair it if it ever breaks down. So
That's on YouTube.
yeah, it's on YouTube now. I gave it 145 or so today. Yeah.
Oh, okay.
Yeah, Greg, thanks for that because Scope Stuff has a lot. I've gone to Scope Stuff. They've got you posted on in your lecture. They've got a lot of good items there. They've got kind of like the overflow, and it's a good resource for getting that stuff.
Yeah. Thank you.
Hi, Bob Garfinkel. Can't hear me.
Who's calling me?
Just said hi. It's Rick Hill.
Oh, hi, Rick.
Somebody's got some music.
Somebody has music on.
I think it's Rick.
Yeah, I got to turn it off. There we go.
Or I can just mute you. I'll just do that. It's a lot easier.
I'm impressed with the speaker that you could hear it with the microphone.
Sounded like good jazz to me.
Pretty much.
All right, I'd like to get started. I'd like to welcome everybody to our awards meeting and also our keynote speaker with Dr. Paul Sutter. I see him in the audience. Welcome, sir. I just want to start off by thanking everybody for a wonderful conference of 2 days. Great lectures. Everybody's been talking about the different ones they enjoyed most and all the great speakers. I also want to thank Ken Pachedli and Jim Tomney for their assistance over the 2-day event and up to that, up to starting the whole thing. So our awards. The first award we're going to give away today is the Mike Reynolds Award. This award is presented to an individual for significant contribution to popularizing astronomy, recognizing their outstanding contributions to the public understanding and appreciation of astronomy. We've only had 2 recipients of this award in the past, Prenvera Hysini for her work in Kosovo and building the only national observatory in the country, and to Scott Roberts from Explore Scientific for the work he's done for many years, working with Meade, working with all the other telescope manufacturers, and how he's served the amateur astronomer. This year's Mike Reynolds Award goes to David Levy. Unfortunately, David can't be here tonight. We will present this with him at a later date. The 2025 recipient is a Canadian astronomer, science writer who co-discovered comet Shoemaker-Levy 9 in 1993, which collided with the planet Jupiter in 1994. Levy was born in Montreal, Quebec, Canada in 1948. He developed an interest in astronomy at an early age. However, he pursued and received a bachelor's and master's degree in English literature. And if you want to go back in time, a couple of years ago, I had David on the podcast, and we talked about Shakespeare. We didn't talk at all about astronomy. So it was a lot of fun to take him on that path. Levy went on to discover 22 comets, either independently or with Gene and Carolyn Schumacher. He's written 34 books, mostly on astronomical subjects, such as The Quest of Comets, a biography of comet discoverer Clyde Tombaugh in 2006, and his tribute to Gene Shoemaker in Shoemaker by Levy. He has provided periodic articles for Sky and Telescope magazine, as well as Parade magazine, Sky News, and most recently, Astronomy magazine. He's also the past coordinator of the Comet section for the ALPO from 1984 to 1988. And his award reads, Michael D. Reynolds Astronomy Award, 2025, David Levy, in recognition for your extraordinary dedication to astronomy outreach, your ability to inspire wonder through storytelling, and your lifelong mission to connect the cosmos to people of all ages. Through words, discoveries, and passion, you have brought the stars a little bit closer. Congratulations, David. Now you can unmute and applaud. Okay, the second award we have is the Peggy Haas Service Award. Hang on here. Okay. Peggy Haas Service Award was established in 1997 to recognize members of the ALPO for outstanding service to our organization. The current ALPO Executive Director, Ken Pachedli, solely selects the recipient for this award, which can recognize any ALPO member, board member, volunteer staff member, or non-staff member who has contributed outstanding service to the organization in the capacity excluding observational astronomy. Observing skills are recognized by the Walter H. Haas Award. The Peggy Haas Award is not necessarily an annual award, but presented when it's appropriate and is not specific to any time interval. The award itself consisted of a grave plaque, and the awardee also receives a lifetime membership to the Association of Lunar and Planetary Observers. This year's winner, Jim Tomney. In 2020, Jim stepped into the leadership role as the assistant coordinator of the ALPO online section, where he leveraged his professional background in software development to modernize and enhance the organization's digital presence. One of his key responsibilities has been curating and managing the ALPO's extensive online galleries, which house over 36,000 sketches, drawings, images that are submitted by members from around the world. His meticulous indexing and dedication to this task ensure that these valuable resources remain accessible. In fall 2022, Jim embarked on an ambitious project to redesign the ALPO website, recognizing the need for a modern, mobile-friendly platform that could better serve its members, attract new enthusiasts. He worked tirelessly to reimagine the site's design and functionality. The new site launched in the summer of 2023 and to widespread praise for its sleek interface, improved usability, and enhanced access to the ALPO's wealth of resources. Jim's redesign was more than cosmetic. It was a forward-thinking transformation that positioned the ALPO to thrive in the digital age. As the organization grows, Jim continues to add new features and fresh content, ensuring the site remains a vibrant hub of the global astronomy community. And the Peggy Haas Service Award 2025, Jim Tomney, an appreciation and recognition for outstanding dedication and invaluable contributions to the online services of the Association of Lunar and Planetary Observers. Your tireless efforts, in-depth research, meticulous work in developing and advancing the new online platform have greatly enhanced the accessibility and functionality of the ALPO website. Your expertise, responsiveness, and commitment are deeply valued and reflect the highest standards of our organization. Your work has resulted in a much smoother experience for those contacting the ALPO via its online experience. The ALPO recognizes and values your expertise and commends you and your dedication.
Congratulations, Jim.
Congratulations.
Thank you. I am humbled and so appreciative of not just the award, but of the feedback that I've received from everybody with what we've done with the website. And, I see a lot of people on here right now that contribute regularly to the website and help make it what it is. And I look forward to continuing to do that. Again, thank you, Ken, Tim, and everybody for the award. It'll definitely find a prominent spot here at my house. So thank you very much.
It's well deserved. Congratulations, sir.
Thank you.
Hey, Jim, congratulations from Ron.
Thank you, Ron.
All right. And our final award this evening, the Walter Haas Observers Award is bestowed annually. Pardon me? Oh. The Walter Haas Observers Award is bestowed. Everybody on mute, please.
So
who's not muted?
I'm eating dinner now.
Okay, Richard. Thanks for sharing. The Walter Haas Observers Award is bestowed annually to an amateur astronomer for excellence observational solar system astronomy. This award is named for our founder and original executive director that was established in 1985. The selection of this award is conducted by a committee convened by the committee chairman, which happens to be me. I've done this for the last, 5-7 years, something like that. The composition of the committee changes from year to year so that the responsibility of selection is shared by a wider group of members of the ALPO that are well qualified, while allowing others that vote 1 year to be considered for the award in another year when not serving on the committee. I'd like to thank the 2025 members of the Walter Haas Award Committee: Richard Schmuty, Clyde Foster, Bob Lunsford, Frank Maleo, Trevor Berry, and Matt Will. This award is given for excellence in solar system observational astronomy. The award itself consists of an engraved plaque, and the awardee also receives a 2-year complimentary to the ALPO. This year's recipient is Greg Chanos. Greg became a member of the ALPO in 2021. He has submitted over 500 planetary images. He lives by the philosophy of, if it's clear out, I must observe. Greg's images of planets frequently appear in the Strolling Astronomer. Mars observations during 2023 operation were analyzed for blue clearing by Dr. Roger Venable, and the results published in the winter 2025 issue of the Strolling Astronomer. Greg frequently submits his images to the Moon and the Lunar Observer and Comet News as well. And the award reads, Greg Chanos, in recognition for your contributions to the ALPO, specifically in the field of photographing the planets with filters, Greg has become a valuable asset to the ALPO, readily sharing his knowledge and expertise in photographing the planets in infrared, ultraviolet, and other wavelengths to reveal details not seen in visible wavelengths. His lectures at ALPO conferences, such as this one here today, and on YouTube webinars have generated great interest. ALPO members have also commented on his one-on-one correspondence to help them become successful in their own photographic pursuits. The ALPO recognizes and values your expertise and commends you on your dedication to our organization. Congratulations, Greg.
Oh, wow. Oh, my God. That's a dream come true. Thank you. Thank you very much. Oh, wow.
Well, I've done this for, like I said, 6 or 7 years, and there's always been a pack of people that could get the award.
Yeah.
Well, you jumped onto the scene a couple years ago, and all of a sudden your name went right to the top of the list. So, congratulations, sir. I really
thank you very much. I'm honored. Oh, wow, this is great.
Yeah. Okay. So now I guess it's time for our keynote speaker, and I'm going to hand it off to Jim for the introductions.
Alrighty, let me get myself off of mute here. So Paul M. Sutter is a cosmologist at Johns Hopkins University and an advisor to NASA's Innovative Advanced Concepts program. He's a prolific scientist and has written over 60 academic publications on topics such as the earliest moments of the Big Bang to the largest objects in the universe. Paul's also an award-winning science communicator. He's authored 3 critically acclaimed international best-selling books and has hosted television shows on Discovery, Science Channel, History Channel, and numerous other digital outlets. You can often find his essays in the New York Times, Scientific American, Nautilus, and others. In addition to regular appearances on NBC News, BBC News, CNN, and the Weather Channel, Paul has developed one of the most popular podcasts in the world and is a globally recognized leader in the intersection of art and science, especially in his role as a United States Cultural Ambassador. So what is Paul going to be talking about this evening? What would it take to plant crops on Mars? What kind of strange life might exist in the outer reaches of our solar system or on planets orbiting other stars? What does life need to succeed, and why haven't we found any outside of the Earth yet? In his whirlwind tour of the cosmos this evening, we'll explore unexpected places where life may have gained a foothold in the distant past and might still persist today. We'll see how NASA's latest instruments, like the James Webb Space Telescope, are on the hunt for signs of alien life. And we will venture to the most extreme and exotic habitats imaginable, like globe-covering oceans locked under miles of ice and planets where the sun never sets. So, Dr. Sutter, if you would please, you have the floor, sir.
Oh, thank you so much for the wonderful introduction and the opportunity to speak to all of you tonight. I am a cosmologist. I'm a theorist. I love studying the earliest moments of the Big Bang, the largest structures in the universe. But like you, I'm curious about just about everything in the night sky, which is why I wanted to present to you not something based on my research, but something that I am personally fascinated by, something that I am drawn to, something that I like to read about, something that when I am confronted with a gorgeous, deep, unpolluted dark sky, which I've had the privilege a few times in my life to have a completely unpolluted sky above me. The kinds of questions that I like to ask, and I like to ask some of the big cosmological questions, like where does it all come from? Where is it all going? And I also like to ask that fundamental question of, are we alone? Is there life? It doesn't have to be intelligent. We don't have to talk to it. It could be a microbe. It could be a strand of DNA or RNA that is self-replicating and having a great time doing it. I just want to know, with the thousands of stars that we can see with the unaided eye, with the trillions upon trillions of stars behind them, is what happened here on the Earth, the story, this something special that happened on our own planet billions of years ago and continues to persist to the present day, is that story told somewhere else? And the story I want to share with you tonight starts in, of all places, Antarctica. And I want you to imagine walking through above the Antarctic ice sheet, where there is nothing from horizon to horizon, maybe a top of a glacier-covered mountain peak in the distance. That's it, just a complete bare plain. And sitting on that plain as you walk, you encounter a small black rock. And this small black rock is actually very special. There's one in particular that we care about called ALH 84001. This rock comes from the Allen Hills region of Antarctica, hence the name. And it's not a very big rock. It's not a very heavy rock, but it is a very special rock because this is a meteorite, and Antarctica is a favorite hunting ground for people who collect meteorites because, you know what? The meteorites have been falling on Antarctica for hundreds of millions of billions of years, as long as there have been ice sheets there. And sometimes they just sit out on the surface and you can spot them by eye because the rocks are dark and the ice is not. And so you can just walk along and find meteorites. So some of our most scientifically valuable meteorites come from the ice sheets of Antarctica. And this one in particular, though, isn't just a normal meteorite. This is actually a piece of Mars that was broken off by an impact billions of years ago. Then this fragment got ejected from the surface of Mars, spent who knows how long wandering around the inner solar system, and then fell to Earth, landed in Antarctica, ended up on top of the ice. And in 1986, we grabbed that rock and stuck it in a laboratory. And then 10 years later, a team of scientists were investigating this rock under a microscope, and they found something absolutely remarkable. They found these structures, these patterns, these things that, honestly, if you were just to show me this picture and I had no idea about the history of this rock or anything, you say, what am I looking at? I would say, this looks like an electron tunneling microscope image of a little worm thing, maybe a fossil of a worm, maybe a tunnel carved out by a living creature. This looks alive. This looks like the product of something alive. Now, this feature appearing on this rock set off a firestorm, and I'm sure some of you remember in the mid-90s, Bill Clinton gave a speech, NASA press release, a firestorm in the media, that maybe we have found evidence for past life on Mars, that we have found a fossil from a Martian meteorite. Now, as these stories tend to go, after the initial splash, the real hard-nosed skeptics came in, the other scientists came in, and it started to pick apart these findings. And what they found was, yes, there are living creatures that could produce structures like these, but usually living creatures produce structures that are much, much larger. And there are chemical processes that can lead to these tube-like features where, trust me, chemistry is super interesting, but not quite as interesting as biochemistry, not quite alive. So it didn't quite meet that threshold, but it got us talking more seriously, not about life on Mars today, but life on Mars in the past and whether we could find evidence for that life. Now, Mars is interesting. We know that around every star, there is a special region called the habitable zone. The habitable zone around a star is where there's just enough heat and radiation coming from the star to create the conditions necessary to have liquid water on the surface of a planet. It doesn't guarantee liquid water, but all we know is that it's not too hot for the water to evaporate and not too cold for it to freeze, that there can potentially be liquid water on a planet. And when we perform those calculations for the sun, the habitable zone of the sun includes the Earth, because obviously, here we are. It also includes Venus on its inner edge, and it includes Mars at its outer edge. Mars is in the habitable zone of the sun. If conditions were right, Mars could have liquid water, bodies of liquid water on its surface. Now, we've been to Mars. We've taken pictures of Mars. I'm sure you have made detailed observations of the surface of Mars. There's not a lot of water going on. It looks like a cold, frozen, barren desert because it is a cold, frozen, barren desert. There is little to no liquid water on Mars, but that's today. The Mars of today is not the Mars of the past. Mars has changed dramatically since the solar system formed 4.5 billion years ago. And we can reconstruct what we think Mars may have been like because we see the evidence for past water on Mars all the time. We see dried riverbeds. We see sedimentary rocks that could have only been formed underwater. We see river deltas in channels. We see everywhere we look that this planet was once wet. And billions of years ago, Mars very well have looked like this. This reconstruction takes all the low-lying areas and floods them with a finite amount of water. And this is the world you get. We know that billions of years ago, Mars was wet. It had a thicker atmosphere. It had oceans, rivers, streams, rain, the whole deal. We know that billions of years ago, Earth was alive, that life got started on Earth pretty much as soon as it could, as soon as conditions were met, basically as soon as our magma cooled, as soon as our mantle cooled and our crust cooled and we developed oceans and continents, boom, pretty much life appeared almost immediately, at least geologically speaking. And at the same time, Mars was cooling down. Mars was separating. Mars was differentiating. Mars was hosting warm, liquid water oceans. But then Mars died. Mars died roughly 3-ish billion years ago. And it died because it was always fated to die, honestly. Mars is too small. Mars can't retain heat in its core like the Earth can. Once the Martian core cooled off, it solidified. And once it's solidified, its magnetic field shut down. And magnetic fields are literal force fields that protect atmospheres from the ravages of the solar wind, the stream of high energy subatomic particles constantly emanating from the sun. With something like the Earth, we have a strong magnetic field. It channels, it funnels, it deflects the solar wind, it protects our atmosphere. Once Mars lost its magnetic field, the solar wind blew away the Martian atmosphere like dandelion in the wind. With the atmosphere was gone, the air pressures dropped, the water sublimated, and Mars dried up. So our question about Mars is we know that billions of years ago, Mars and Earth looked very similar. Earth developed life pretty much as soon as it could. Maybe Mars developed life as well. But then the planet itself died, it dried out. So does any remnant persist? Is there any fossil left on Mars that we could dig up and find evidence for past life? Or perhaps more tantalizingly, is there any form of life that is still eking out an existence on Mars somewhere? Did life flourish like it did here on the Earth? And then as the planet died over the course of hundreds of millions of years, that life adapt and evolve to still survive in some niche somewhere on this dead planet. Now, life is kind of needy. Life needs a lot of things to be alive. Number one, all life as we know it requires water. You need liquid water. It can't be frozen and it can't be in gas form. It has to be liquid. Water is the universal solvent. It is the playground. It is the stage where chemicals can combine, can recombine, where temperatures can be regulated, where fresh nutrients can be brought to you, where waste can be eliminated. You need all that, the activity of life, to happen in a medium, to happen in something. And water is fantastic at doing that because it has so many wonderful properties. And water is super common. It is the most common molecule in the entire universe. The hydrogen from water comes from the first few minutes of the Big Bang. Oxygen comes from the death of stars like our sun, and stars like our sun are pretty common. So you got a lot of hydrogen, you got a lot of oxygen, you bring those together, you get a lot of water. But liquid water is a little bit harder to come by. Second, all life that we know here on the Earth requires an energy source. It could be the sun, it could be hydrogen in some exotic cases. I'll talk more about that in a little bit. It could be chemicals leaching out of undersea vents. There are many, many potential sources of energy for life, but life needs a power source. We are highly organized systems of molecules that are constantly shuffling and back and forth. This needs a power source. This needs energy. Almost all life on Earth is derived energetically from the sun. When you're eating a cheeseburger, you're just eating reconstituted sunlight. There are some forms of life here on Earth that don't need the sun to get by. They are few and far between. The vast majority of life here on it requires the sun, which is easy to see why, because it's really bright. It's there all the time, lots of energy. The sun emits an enormous amount of energy. It is almost hard to describe how much energy the sun emits. To give you some picture, in 1 second, the total amount of energy emitted by the sun could power all of humanity's energy needs for the next 650,000 years. That's in 1 second. Now, only a tiny fraction of the sun's total output actually intersects the Earth, but even that tiny fraction powers the intense variety of life that we see on the Earth. But it's not just water. It's not just an energy source. Life also needs good physics. It needs the right temperature ranges. It needs the right pressure ranges. You can't have like cosmic rays coming in, snipping apart your genetic material all willy-nilly. You need to be in a container. You can't be out in the vacuum of space. You're going to have a hard time doing all the stuff that life likes to do. So life needs good physics, and life needs good chemistry. It needs nitrogen. It needs oxygen. It needs silicon and carbon. It needs to pull on various elements to build itself, to activate, to be able to store, capture energy, store it, transport it, release it later. It needs the right chemical balance of the stuff it needs, and it needs not a lot of the stuff that is toxic to life. So for life to be alive, as far as we understand it, it needs water, it needs an energy source, it needs good physics, and it needs good chemistry. And so we can ask this question: is there any place on modern day Mars, the Mars of today, where these conditions are met? Is there anywhere on Mars where there's liquid water, where there's access to an energy source, where there's good physics, and where there's good chemistry? And surprisingly, there are 3 candidate locations on Mars that might, stressing might here, the word might is doing a lot of heavy lifting here. There are 3 places on Mars that might host life today, that might meet these 4 conditions. One place is underneath the polar ice caps. These ice caps are so cold, they're actually mostly frozen carbon dioxide. They are dry ice. There's also water ice in these polar ice caps. And some radar mapping of the ice caps shows that underneath in patches of these ice caps, buried like a mile under the glaciers, there are some highly reflective regions that might be suggestive of subglacial lakes, liquid water lakes buried deep under the ice. Now, we know these happen on the Earth, so it's not inconceivable that they can happen on Mars, that the weight of the ice cap essentially acts as a pressure dome to be able to keep that water liquid. It might be incredibly salty. It might be full of chemicals that are not so great for Earth-based life. They might not. We don't know yet. Another interesting candidate for the appearance of potential home for life on Mars is something called recurring slope lineae. These are these dark streaks that appear in crater walls. And during the winter months, these streaks appear, during the summer months, these streaks appear, and then during the winter months, these streaks disappear. And so they follow a seasonal pattern. We're not exactly sure what is causing the dark streaks. One possibility is that this is water either leaching out of the soil or being captured from the atmosphere and then running downhill. It's like making a moist slurry that then gravity that just pulls down the crater wall. Another possibility is that these aren't wet in the sense they're more like moist, like a slightly moist sponge, but that's enough to give them this discoloration. And another possibility is that it's just ices of various compounds that appear in these shadowed regions in one season, and then tumble down to make a streak in another season. There are a lot of possibilities here. We're not exactly sure what is going on. And the last possibility for where life might exist on Mars is actually nowhere near the surface, but deep underground. There are regions roughly 1 to 2 kilometers underneath the surface of Mars, in especially the northern hemisphere, where temperatures are very interesting. It's hot, but not too hot, where there might be the conditions where there could be little microscopic bits of water trapped in with the rocks, like in tiny little crevices and tiny little fractures within the rock. We don't know. We do know that on the Earth, life has found a way to live a kilometer or two below the surface, deep in our crust, existing in these tiny little cracks of water, in these tiny little microscopic pockets of water. There are single-celled organisms, and in some cases, some multicellular organisms that do live there. They obviously don't get their energy from the sun. They actually get their energy from consuming hydrogen, and they expel methane as a byproduct. And they do it. We know of these kinds of organisms here on the Earth, and the presence of life deep under the surface of Mars might explain some strange observations we've been having on the surface of Mars for the past couple decades, where we do see seasonal variations in the levels of methane in certain patches on the surface. We don't really see it globally, but landers and rovers have detected this seasonal variation where in the summer months there's more methane, the methane spikes, and then during the winter months it fades back down. Right now, we really don't know what causes that seasonal variation of methane on Mars. One potential, and again, I stress potential explanation, is that there might be a community of single-celled organisms living under the surface of Mars that are consuming hydrogen and expelling methane, and that
This is
they are more active.
Picture describing what they think is.
They are more active in the summer months, just like most things on Earth are more active in the summer months, and then they hibernate a little in the winter. So this is very hypothetical. It's just a guess now, but these are three very intriguing places of where we want to study more. But like I said, Mars is not the only planet in the habitable zone of the sun. There's also Venus, which is on the inner edge of the habitable zone. Now, we don't know for sure if Venus a long time ago hosted oceans like Earth and Mars did. We suspect it did because Venus is made of pretty much the same stuff as the Earth, has pretty much the same size and composition. So it'd be very strange for Venus not to host a lot of water like Earth and Mars did. But Venus is a dead world just like Mars. If you've ever seen it, it appears as the morning or evening star. This is actually a false color image to show you some of the variations in the cloud layer. If you were to look at it up close, if you were to be this far away from Venus, say you were in orbit around Venus, and you were to look at it with your naked eye, it would actually be bright enough to blind you. It would just appear as almost as bright as a star because it is so highly reflective. And that's because of these incredibly thick atmospheric layers. Unfortunately, what happened to Venus is a runaway greenhouse effect in its early years, where as the sun ages, it tends to get a little bit warmer over the course of hundreds of millions of years. And it just got a little bit too hot for Venus, where it boiled its oceans, went into a domino effect where the greenhouse effect just cycled over and over and over again, raised the temperatures on the surface through the roof. As the planet dried out, it shut down any plate tectonics it may have had going on. And then that prevented carbon from being sequestered down into the crust. And so there was just another feedback cycle where carbon built and built and built up into the atmosphere, and then it choked the planet to death. And so the surface of the planet is not so great. These are images from the surface of Venus. The Russians were able to send the Venera probes down there in the 1970s. Nobody's been back since. Each probe lasted for dozens of minutes at most, because the surface of Venus it's actually the hottest surface in the entire solar system. It's hotter here than it even is on Mercury, even though Venus is roughly twice as far away from the sun. Peak temperatures here are over 900 degrees Fahrenheit. Even the low temperatures here are hot enough to melt lead. So, of course, our spacecraft are not going to last very long. And good luck. I know life can find a way. Life can be very surprising, and we have a lot to learn about the nature of life. But good luck finding a way for living organisms to sustain themselves in this kind of environment, because it's so hot, the pressures are so high, it's so inhospitable that the basic chemistry, that even the craziest kind of life that you can imagine, at the end of the day, you're going to need chemistry, and chemistry is really, really tough here on the surface of Venus. But there's more to the story of Venus than just the surface. Just like Mars may have incubated life in its early days, then as the planet froze, maybe that life migrated beneath the surface to find a way to live. Maybe life here started on Venus as well billions of years ago, and as the planet heated up, it found a way to live in the atmosphere on Earth. Just like we know of single-celled organisms and microscopic critters that can live a mile beneath the surface, we see free-floating single-celled organisms floating for miles high in altitude in our own atmosphere. And when we look at the atmosphere of Venus, we find that at a certain altitude, right around the 50 to 100 kilometer range, Once we get up above the volcanoes, once we get up above the sulfuric acid cloud layer, when we're in that range, the temperatures are room temperature. The pressures are sea level pressure. It's actually kind of nice. I mean, yeah, there's the sulfuric acid atmosphere and poisonous toxic atmosphere that would literally dissolve you if you were to encounter that. But take that away, and the upper atmosphere of Venus is actually kind of balmy. So there have always been hints that maybe something funny could be happening here in the upper atmosphere of Venus. And a few years ago, there was a big announcement of the discovery of a chemical called phosphine. Phosphine is a byproduct here on Earth of anaerobic respiration. It's a very stinky gas. It's one of the reasons that swamps smell kind of bad, because there's a lot of phosphine in the atmosphere. There was a claimed detection of significant amounts of phosphine in the upper atmosphere of Venus. Now, the thing about phosphine is that it's very susceptible to UV radiation. Ultraviolet light from the sun can just break it apart. So for there to be a lot of phosphine in the atmosphere of Venus means that it has to be replenished. Because if you're to just say to have like a singular volcanic event that spills a lot of phosphine into the atmosphere, very quickly it will break down. You shouldn't see it if you just go make some random observation. You don't expect to catch one of those special events. So if phosphine is present in the atmosphere of Venus, that demands an explanation. One potential explanation is that maybe, just like on Earth, it is a byproduct of life. Now, those results, I do have to say, are highly disputed and argued over. The original result has been shown to be incorrect. The actual amount of phosphine on Venus, if it is there, is actually much less than what the original study found. It's also possible that it can be confused for the presence of carbon dioxide. There's a lot of argument over the data analysis techniques. And then, once again, just because we see phosphine doesn't mean that life is the thing making the phosphine. There's certainly some weird, funky chemistry happening on Venus. Maybe some of that is producing phosphine as a byproduct. Some chemical process that is not easy to replicate on the Earth or in laboratory, some process that we have not figured out yet. Just like on Mars, just because you see the methane, or more appropriately, smell the methane, doesn't mean that it's guaranteed to be a byproduct of life. But that's the inner solar system. And if we were doing traditional astronomy, just caring about habitable zones, just caring about creatures living on the surface of a planet, that's where we would stop. We would look at the habitable zone of the sun and be done with it. Yeah, there are other planets like Jupiter, Saturn, Uranus, and Neptune, but they're gas giants, they're ice giants. And yeah, maybe you can envision some crazy form of life that like lives deep within the clouds of these planets. But you know, for all intents and purposes, they're relatively inaccessible. We're not going to find out anytime soon if those worlds are live. But the solar system has a lot of surprises in it. And one of the surprises is Europa. This is the second largest moon of Jupiter. It's the second moon of Jupiter. It's the second one out. And from orbit here, Europa is strikingly beautiful, but also dead. It's covered in this thick ice sheet. It's streaked with these cracks and canyons. There's this smattering of red molecules we call tholins. But it's frozen. That's water ice. You're looking at water ice. You could chip a few blocks off and put it in your drink if you wanted to. I can't guarantee. No promises made about what it will taste like, but you could do it. It's just water ice, which is pretty dead. But Europa has a secret. Because of its unique orbit around Jupiter, it actually stretches and squeezes as it orbits around Jupiter. And this flexing internally heats it up. And so the core of Europa, of this moon, is actually molten, the same way that the core of the Earth is molten. And so you have a situation where you have water ice on the outside and a heat source in the middle. And what this gives you is an ocean, a globe spanning liquid water ocean. This ocean is completely unlike anything we have on the Earth. This ocean is completely locked away from the sun. It is the thickness of that ice sheet is around 100 kilometers, give or take. So there's absolutely no sunlight reaching this ocean. The ocean itself has a depth of about 100 miles. It completely spans the globe of this entire moon. Even though Europa is a small moon, it has more liquid water than the Earth does. We are well outside of the habitable zone of the sun. We are well outside any place where liquid water can exist on the surface of a world. But this is something different. This is a vast liquid water ocean. So we've met the first criteria, which is liquid water, but we need more than liquid water if we want to make something alive. And we have a clue here. Again, we can look to the Earth for analogies for what kinds of life might live in the solar system. And the analogies we find here are the deep sea hydrothermal vents. If we go miles beneath the surface of the ocean, well beyond the reach of sunlight, we find these chimney-like structures that we call black smokers. These are vents in the crust of the Earth where magma can come up, superheat the surrounding water, which then pipes upward. And as it pipes upward, this is fantastically mineral-rich water. These are really heavy with tons of different minerals. And actually, microorganisms can feast on those minerals, extracting the heat energy from these vents and do all the things that life can do without any access to the sun at all. And from there, we have entire ecosystems, entire communities of tube worms, of crabs, of fish that all are based on a completely parallel food chain, one that does not originate from the sun, but originates from these deep sea vents. This is happening on our Earth right now. And so the question for Europa is, does it get deep sea vents? Does it have a source of energy? And it all comes down to can the core, the molten material in the core, can it reach all the way into that ocean? Can it come up from the bottom and actually punch through the mantle and make its way to the ocean? This is a major unsolved problem. NASA, both the European Space Agency and NASA, have spacecraft on the way to study Europa. The Europeans have the JUICE mission, the Jupiter Icy Moon Explorer, and NASA has the Europa Clipper. They are both en route to Jupiter right now, and they are going to study Europa. Now, we don't have the technology yet to drill down through that ice and send submersibles through this ocean to check it out for ourselves. But the nice thing about Europa is that there are these cracks in the ice where water can squirt out. We call them cryovolcanoes. They are frozen volcanoes of where the water actually comes out of the ice or ejects up into space. And by studying those, we hope to get a better handle on what is going on inside of those oceans. If it definitely has liquid water. There might be an energy source, and it might have the right physics and chemistry to make life possible, but we don't know. And I want to give you one more surprising place in the solar system, which might be a home for life. It's out here in the outer solar system, and it's a moon of Saturn. It's the largest moon of Saturn. It's Titan. I'm sure many of you have seen Titan through your telescopes. Now, Titan is a very, very strange world. Titan is actually covered in a very thick atmosphere, which is surprising because we're kind of far out from the solar system, and Titan isn't all that big. but it has a thick atmosphere. And in fact, aside from Earth and Venus, it's the only rocky planet in the entire solar system with a thick atmosphere. And believe it or not, we've actually taken direct samples of this atmosphere because we sent the Cassini spacecraft to Saturn. And on board Cassini was a little hitchhiker called the Huygens probe. And Huygens detached from the Cassini spacecraft and actually parachuted through the moon of Titan, through the atmosphere, and actually landed on the surface. This is an image, an aerial view of a mountain chain with some plains from the Huygens lander during its descent. And then this is a picture of the surface of Titan sent back to us from the Huygens probe. And what you're looking at here is a vast plain of frozen nitrogen. It is so cold here. We're talking roughly negative 270 degrees Fahrenheit. It is so cold here that nitrogen itself freezes. Those boulders that you see aren't stones. Those are actual chunks of frozen carbon dioxide and frozen water ice that are strewn about this nitrogen plain. But what's most surprising about this world is that there are liquids here. We have direct observational evidence of liquids, large bodies of liquid on the surface of Titan. This is an artist's rendition of what those liquid lakes might look like. They're large, not quite ocean level, but like Great Lake-ish in terms of scale of the moon, this moon, Titan. Now, these lakes are not liquid water. Liquid water is not happening here at negative 270 degrees Fahrenheit. This is liquid methane, liquid propane. These are liquid hydrocarbons. These molecules can exist at extremely low temperatures. So we have a planet whose crust is frozen nitrogen, whose boulders are frozen carbon dioxide. This world has an incredibly thick hydrocarbon-rich atmosphere, and then there are stable bodies of liquid. On this surface, it is the only world other than the Earth to host liquids of anything, of any kind, in any permanent capacity on its surface. This is both exciting and horrifying because, yes, it is a potential home for life. We have a liquid, we have an energy source, maybe we have the right physics and chemistry. It's also horrifying because this kind of life would be completely unlike any life we have encountered ever on the Earth. So the one thing that all life on the Earth has in common is that it uses liquid water as a solvent. Titan, the surface of Titan, does not have liquid water. It does have liquids though. So this opens up the question, can there be a form of life on Titan that uses liquid hydrocarbons, methane and propane, as its solvent, as its base, as its playground, as its stage? And if so, what kind of chemistry is happening here? And is it a biochemistry? There have been a lot of studies. There have been a lot of work in this direction. It's all theoretical. We don't know for sure. We have not, besides Huygens, we have not sent a direct probe back to Titan. There is a proposal, NASA's Dragonfly concept is hoping to go to Titan and hop from landing site to landing site and hopefully visit some of these oceans and our liquid seas. We don't know. It might be possible that life can build a complete biochemical pathway that uses methane as a solvent, uses hydrogen as an energy source, uses some of that ultraviolet light filtering in from the distant sun as a power source. We just don't know. But if whatever is happening here on Titan is definitely very strange and very surprising and very unexpected, And that's one of what my favorite part about the search for life is just how unexpected it all is. That every time we think we have come up with a complete definition of life, that we have come up with a nailed down way, like, okay, this is how we look for life in the universe. We do this, we do that. Sorry, my perfect way to cap the end of my talk. I don't know if you can hear that. My cats have an automated cat feeder here in my office, and it is calling the cats in to come in for dinner here at the end of the talk. So that is a perfect way to end, because we are not alone in the universe. We have our cats, we have each other. We might have, space whales on Europa and weird critters on Titan. We do not know. This is an active area of research. This is something that we are all fascinated by, and only time and a lot of research and a lot of work will be able to answer this question for us. So thank you again for sharing your time and space with me this evening.
Thank you very much. Open it up for any questions for Dr. Sutter.
Thank you, Dr. Sutter. Thank you very much. Entertaining, informative, the kinds of things that I think can get students energized, jazzed about just science in general, or especially about life on other worlds. Let me ask, though, if I may, what do you anticipate? You say the missions are en route to Europa. What would, if you were on the team, what would you want to get to see first in scanning, whatever instrumentation? What would you want to inspect first when you arrive within closer to the vicinity of Europa, to want to check first for the prospect of life? Just curious.
What we want to check first is for one of these active plumes, which just have to happen randomly. So we're going to have to do a lot of orbits, wait for a plume to start. Hopefully we can actually swim through one of the plumes as it goes, but at the very least we'll be able to do some remote observations of the plumes and get detailed spectroscopic analysis of those plumes. If we're lucky, we find an evident biosignature, but at least what we're hoping to find is a lot of oxygen, maybe a lot of dissolved carbon dioxide, maybe some concentrations of heavier elements, of some mineral content, just something that gives us a picture of what that ocean is like, because it could be alive with a lot of rich chemistry. It could also just be absolutely sterile and super saturated in like arsenic, where it'd be very difficult for biochemistry to proceed. So what we need to nail down is, what is the chemistry of that water?
Thank you.
Of course.
Paul, I was about to ask you, I'm bothered by the question of how we would recognize life if we found it. In order to frame this question, consider that we're out on, Titan, where the temperature is minus 270 degrees Fahrenheit, and therefore the amount of energy that life would have to work on, between the high energy state and the low energy state, that's where we all live. And it would be a very small amount of energy, which means life would be very, say slow. In other words, it wouldn't move much, it wouldn't be able to reproduce fast, and so on. And so for that reason, it might be extremely difficult to identify anything we would call life. And I just wonder if you've dealt with that issue.
Oh, that is a very, very valid concern. And this definitely keeps a lot of researchers up at night, is answering this exact question, especially when it comes to the further you get away from Earth-like life. Because with Earth-like life, we know what we're looking for. We know those biosignatures. We can see the little tunnels that microorganisms make inside of rocks and so on. We know what they consume and what they expel. But you're absolutely right, with something like Titan, that not only has a completely different biochemical pathway, but is also operating at radically not Earth-like temperatures, there is a lot of discussion about how we would identify it. Like, if you were to stick it in a petri dish, would you actually see something swimming around, or is that not what Titan life does? Is it even composed of cell membranes? Do we even have like anything more than just strands of genetic material that like almost like a protovirus that consume a certain energy source and then expel a certain output and then recombine in interesting ways? This is an open question. I don't have an answer for you, except that this is something that people really, really worry about and want to figure out how to identify. And so it takes a lot of theoretical modeling, a lot of guessing, a lot of, well, let's go out to Titan and see what we see. Let's send the Dragonfly, let's send more probes. And then when we see interesting stuff pop up, if there are things that point to the presence of life, like seasonal variations, like an abundance of an element that should not be there if the planet were in equilibrium, then if there's a sign that there is some activity that is changing the equilibrium of the planet, then we start sending more stuff out there.
I have a question. What about the outgassing on Io?
Right. So Io is also outgassing, the only other volcanically active planet, our world in the solar system, except maybe Venus. Venus might or might not have active volcanoes. But Io is incredibly hot, and it's probably too hot for life. Again, we don't know the extremes where life can originate, where it can persist. But if we're rank ordering our candidates, Europa is going to be a better bet than Io. And so in an era of finite budgets, Europa it is.
Okay. Paul, this is Richard Schmoody. I'm curious about Mercury. Now, Mercury has no axial tilt. And there's good evidence that there's a polar ice at the north and south poles. And I know it's hot at the equator, but how about near the North Pole, say? Do you think there's any possibility maybe underground type of life?
Yeah. Again, yeah, you're right. There are these ice in the permanently shadowed regions of the craters at the north and south. So, hey, water ice is a good thing. It's certainly a step. It means there is water present on that world. Again, there's always a maybe here. Because life can be extremely flexible. The challenge with Mercury is that it doesn't have the geologic history that Venus, Earth, and Mars did. Mercury has always been on the inside edge of the habitable zone. It's always been hot. We suspect it's never had a substantial atmosphere. Anything like water is going to be extremely volatile in the inner solar system. You need a thick atmosphere to contain water on the surface of a planet. So it just doesn't have that lineage that Earth certainly did, that we know Mars did, and that Venus probably did, which just bumps it down in the betting game.
Well, thank you very much.
Of course. Thank you.
You're welcome.
Question about astronomy outreach, Dr. Sutter. I've been doing outreach here in the Atlanta area for over 20 years, and I work at part-time at a science center here in the observatory. So I get a chance to meet a lot of people here, young, old, in between. They've come there many times, sometimes they're first visitors. And so through the eyes of the lenses of a big telescope and through, shepherding them through what they're looking at, it's been great to get their reaction. But I don't see very many people, and in terms of the greater population, whereas someone like you is getting out and addressing many different audiences in different settings. And I'm curious what your impression is of the general public that you talk to, the questions you hear about the interest in science, the interest in what's out there, whether it's alive or just distant, or just something, that catches a lot of headlines, like a black hole or something. But can you give us just a basic impression on what you hear from your audiences in terms of their attitudes and aptitude as far as science is concerned?
Oh, of course. Like I do have somewhat of a self-selection bias here because the people that tune into the shows that I host, who reach out to me after watching the shows, they're already somewhat interested and engaged. But I meet people on the street. I sit next to people on airplanes. Sometimes they recognize me from TV. Sometimes they see me working on my laptop and strike up a conversation. People are interested. People love this stuff. People eat it up. There are TV shows that I recorded nearly a decade ago that still pull in 500,000 viewers on reruns. There's so much love of curiosity. People do wonder what's out there. They are surprised every time they look through a telescope. They are blown away by what they see. People love this. And so I don't want you to be worried if you only see a small fraction of the population, because what you are doing with your outreach is deeply impactful. I still remember as a kid, the first time I looked through a telescope. I still delight in looking through a telescope and seeing cool new stuff for myself. That's an impression that lasts with people. I've seen many people look through an eyepiece and then stand up changed. And so the change that you're impacting on those people is much deeper and much more personal than me like waving my arms around on TV. And so if you change like 10 lives in a night, that is 10 lives that are deeply and profoundly have found a spark, something fascinating about the universe that they will carry with them for the rest of their lives, and that they will tell 10 people, they will tell 10 people, they will carry that memory with them. So just trust that people are curious. The vast majority of people are curious about astronomy. They like hearing about astronomy. It fires the imagination. And the work that you are doing is absolutely critical.
Thank you. That's very encouraging.
All right. Thank you very much. Oh, go on.
Man, just one other quick item. I'm sorry, I didn't mean to interrupt, Tim.
No.
I'm curious. You mentioned terrifically in the habitable zone. Let's go just beyond the high habitable zone a bit further. Some years ago, the Dawn spacecraft returned some interesting results from Ceres, I believe. Any further items, any interpretation on some of the organic molecules that were supposedly found from that mission?
Oh yeah, Ceres has this really interesting history where it looked like something whacked it, and then it looks like something liquidy, probably water, welled up to the surface, and then evaporated and left these like salt-like deposits that might. It's my understanding as well that there might be some organic molecules. As far as I'm aware, I'm sure there has been follow-up and continued studies. But one of the amazing things about the search for life is that we're finding organic molecules like everywhere. We see them in planets in the worlds in the Kuiper belt. We see them in comets, from the distant solar system. We see organic compounds in molecular clouds. We see it in star-forming regions. We see it in protoplanetary disks. It seems that the galaxy is really, really good at making organic compounds, which is very heartening for any discussions about the potential for life out there, but then also discouraging because then you run into that Fermi's paradox issue where, hey, if there are organic compounds everywhere, then where's the kind of organic compounds that we can have a conversation with?
Thank you.
Of course.
Well, it's been my conviction, as with a background in biochemistry and in ecology, evolution, and systematics. I have a double major in biological sciences. It's my impression that life only formed on Earth once. And here we are living in this planet that supposedly is ideal for life, in the habitable zone. We even construct a concept of a habitable zone because it's like ours. And the problem is that if you look at the phylogenetic record, the fossil record, the biochemical record, the DNA and the other proteins in life we call haptones that guard DNAs. We look at their mutation rates in different phyla and so on. We find that the tree of life, as designed by the phylogenists, those who construct the tree of life, are convinced that there's one source of all life on Earth. Now, that doesn't mean that no other life ever formed, but I'll tell you that biologists are convinced that all life that we know of formed from a single source. So the thing is then, if life only formed once on Earth in this ideal location, why would we think it forms in a much, much less ideal location like Titan or Mars?
Yeah, and I think that's a very, very valid question. And a potential rebuttal to that is, what do you mean by ideal? Because our kind of life found that location on Earth millions of years ago ideal, but a different kind of life, a different series of biochemical processes could have found different conditions ideal for that. And even if things are less than ideal, maybe life can still get started. There is so much unknown surrounding abiogenesis that we have trouble reconstructing, like you said, even our own history and the origins of life on the Earth and what life was like in its earliest days, let alone on another planet. There are so many unknowns that it's a wonderful playground for speculation and imagination and scientific research.
Thank you for sharing.
I have just one little comment. If any of you guys have written books, please send me a book on your sky so I can review it for the ALPO. Richard Smootie's sending me his book that recently came out. But any of you other guys, come on. I need books to review. Please send them to me. My address is in the journal. So
I wrote them, but it was a long time ago.
Well, it doesn't matter a long time ago. I don't, some magazines will only do it if it's a year or so, but anything that it hasn't been reviewed yet, we'll do it. We'll get your words out there. So please look me up in the journal and send me, or have your publisher send me a book, anything about the solar system, and we'll get it. We'll get a review. I have more time now on my hands than I used to because Luna Cognita, came out 5 years ago, and I'm writing some other articles, but I can certainly get reviews done. So send them to me. And the other thing, if you've got a podcast, let me know. I'd love to be a guest on your podcast. Hint,
You
hint.
have. All right, we'll get you on. All right, Dr. Sutter, I really want to thank you again for answering all these questions and giving us a very entertaining presentation today. Thank you very much.
Oh, thank you. Thank you again for hosting me tonight.
Great. And again, once again, want to thank all the members of the ALPO for participating in this conference. And I really want to congratulate again Jim Tomney for winning such a fabulous award, well-deserved award. And it's been pretty amazing, this conference. So I want to thank everybody for attending, and we will shut it down now. Thank you very much.